spectroscopy is such an important area of any chemistry. You may have even taken an entire spectroscopy course as an undergrad, but for sure you've seen NMR, mass spec, and some UV vis and some of those techniques in organic chemistry to help you elucidate the structures of some organic compounds. So it's no surprise that it's important for inorganic chemistry as well. So I do expect you in this lecture to have a solid grip on proton NMR spectroscopy, the principles and the symmetry and how it works. So that's a given. But I'm going to expand and look into also other atoms, right? It's not all about proton. You can tune your instrument into other nuclei like phosphorus or fluorine or tin, and so that can be useful, right? And it works the same way it does for proton. And in addition, my focus is on the dynamic processes, right? So you already know from organic proton NMR spectroscopy that some of the groups that rotate, like the methyl groups at the end of an alkane, because they have free rotation, we're told that all three hydrogens at the end in the methyl group are chemically equivalent. And so, but they're not really, because there is no symmetry that makes all three equivalent. But because they rotate, and they are faster than the NMR time scale, that dynamic process isn't detected. And that's useful as well. But we can actually cool down this instrument and detect processes like this Berry pseudorotation that we already discussed when I introduced coordination compounds, right? So any trigonal bipyramid, if it has small ligands, in this case it's not a complex, it's just, but the principle applies. You can have an exchange between square planar and trigonal bipyramidal, so you have axial ligand or position and equatorial position exchange. Here the two fluorines that are axial, they exchange and they end up in equatorial positions here as this process proceeds. And we can use NMR spectroscopy or other spectroscopy like IR spectroscopy to detect that, right? And so the reason I have this as an example is because there is no carbon here. You may have done some carbon-13 NMR, and of course you did proton NMR. So we can still use this. We have phosphorus-31, for example, is an isotope. It's 100% abundance, very useful. And then there's fluorine-19. So those are two isotopes that are active, NMR active, and they're quite useful. and so you would, for example, you would be able to see the difference between the axial and the equatorial fluorines here. If you did fluorine NMR, right? If we did a fluorine NMR, you should be able to see two signals for that. But because this process occurs faster than the NMR timescale, you'll just see one. And then we can actually use cryogenic lowering of the temperature to detect this process, right? So that's what I want to focus on, NMR, as well as the dynamic processes and how we can detect them. So the chapter in the Shriver book is called Physical Techniques. It's more broad. It's probably not the greatest resource, but it is a resource. This is a low temperature IR spectrum of iron pentacarbonyl, which is a 5-coordinate complex that's expected to have trigonal bipyramidal geometry. And so it has two chemical environments, and you expect what we are looking at here, two signals for the carbonyl stretches, right? So we have those 5 different carbonyl groups, and as we know, I'm just going to put in an A here for axial and E. So those are two different chemical environments, and you'd expect them to show up in two different regions, which is what we see here, except this occurs in liquid xenon. Think about how low that would be at 162 K. And now at room temperature, what we see is a single signal here. So at room temperature, we'll see a broad single signal for all 5 carbonyls, and that is due to that Berry pseudorotation. And the energy barrier, or energy of activation for this process, this exchange between equatorial and axial positions, as we see here, is actually very low, 2.5 kilocalories per mole, and it's pretty simple to pick that up at negative temperatures just from the thermal energy, and so that's very low. You have to go to a very low temperature. However, if you are freezing out that motion, that doesn't necessarily mean at like 162K or whatever it was in liquid xenon, that doesn't necessarily mean that this process no longer occurs. That just means that the process is slower than your instrument time scale. All right, so you got to keep that in mind. So what will happen is if you see something like this unexpected, you can lower the temperature of your instrument, and what you will see is you will see a flattening of the signal. So this signal will disappear, and at some point the new signals will grow in. And so if you lower it to the right temperature, you reach a process called coalescence. At that point, you are, in theory, you don't observe any signals, and this is true for NMR and IR alike, if you can get to that point. So at that point, the speed of the process is equal to the speed of your instrument. Okay, so we call that coalescence, and that's an important temperature. But I do want to just focus on NMR spectroscopy and how that relates to some dynamic processes. So for example, you may synthesize a compound, or you may want to figure out the structure or prove the structure. You make a compound, it has this chemical composition, you propose the structure, you run the NMR, and what you see at room temperature is a singlet. What that means is you probably have some sort of dynamic process, or it is worth looking into if you can freeze out that motion. And then sure enough, if you lower it to -98, you come up with the expected two triplets. And so I might ask you on an exam or a quiz to explain the dynamic process, so to propose a mechanism and also assign the signals and explain the multiplicity. So let's roll back, come back to this later. Let's just bring you up to speed on what we want to look at first. So first we are going to look at chemical environments. And so as I said already, it's not all proton. In this case, I'm asking for fluorine. So fluorine 19 is an isotope that's has an active nuclear spin and can be detected. It has a spin of 1/2, which we will look at the significance of that in a minute. For now, I just want to look at the symmetry. We are experts at symmetry, right? And simply predict how many fluorine environments we have for each of these compounds. So if you want, you can pause, you can assign this yourself, and then I will go through this pretty quickly once you're done doing it yourself. Okay, so I'll do 3 and 3 just to have some more space, but this is pretty simple. We have a seesaw, and so we have these two that are chemically equivalent. So this would be one signal, and then these two have a different chemical environment, and so this one has two different signals or two different groups, whichever way you want to say that. So and also important to note, what makes these two fluorines, for example, equivalent is that mirror plane that dissects the sulfur fluorine plane here. That is a plane, and that makes this group equivalent to that one. And you also have a mirror plane here, which makes the two fluorine atoms that are labeled A chemically equivalent. So here we only have one signal. There's an inversion center that makes these two fluorine groups chemically equivalent. The next one, we have these two, and then the one here is different. So we have two signals for that. So this is kind of the foundation. How many signals do you see? And in a minute, we're going to look at multiplicity. Do they split? What can they be split by? You know, you did that for protons. You had doublets and triplets and quartets and heptets and things like that, right? So this next one here, we still have these two fluorines are equivalent. There's a mirror plane here, so I'm going to label them A, and then this one up top is B. So we have two signals Same here. It's getting kind of boring, right? So all 2. If you had to guess, it's 2. But identifying them is important, and so we have these, and then this one B, and here all 4 in this is a square pyramid, and all 4 fluorine atoms are chemically equivalent, and then this one is different. So we have 2 signals, and here we have also 2. And then so what I want to look at next is what kind of coupling we would expect, right? Is this fluorine A going to be split by this fluorine? And that depends on the nuclear spin I, all right? And then there's also a phosphorus that's active, and it can also be split into phosphorus. So we're going to look at all of the active nuclei and what the possibilities are, right? So in general, you use the formula 2Ni plus 1. So for hydrogen had a spin I equal to 1/2 for hydrogen, and then N are the nuclei that it's coupled to. So if you have 2 hydrogens, if you have a hydrogen signal and you have another one here, you have A and you have B, and so you see a signal for A, but it's close enough to be split. What you see is a doublet, and that doublet will look like that with equal height, all right? And that's because hydrogen or a proton has a nuclear spin of 1/2. So what happens is, if I is 1/2, so we have 2 times 1/2 plus 1, see, this will turn into 1. So your formula is simply then N plus 1. That's probably what you looked at, right? So if you have 1 additional nucleus, in this case 1, you will see a doublet. If you have 3, then you'll see a quartet, and so forth, right? You just take the number of nuclei and add 1 to it. But that's not always true. You can have boron and you can have deuterium. They have different spins. So we have to actually look at this formula here, 2Ni plus 1. So let's take a look at some examples. Let's make them simple. I am going to look at spin 1/2. And so if we have a chemical environment, like I said, HA, it's split by a different hydrogen, and you see a doublet. And it's also important to note that the height of this doublet, that these are equal, all right? If you have 2 nuclei, 2Ni plus 1, like I said, N plus 1, so it's 2 hydrogen atoms that HA is coupled to, you see a triplet, and they are actually in a 1:2 ratio, and I'll show you how that works in a minute. Actually, why don't I do that right now and come back to that, right? So it's actually, if you draw Pascal's triangle, probably remember that, the intensity or relative ratio of the multiplet corresponds to Pascal's triangle, okay? So a doublet here will have a 1-to-1, it will be equal height. A triplet, the one in the center, will be twice as high, all right? So this will be twice as high, and then this will be 1 to 3 to 3, your quartet here, right? So here we have a quartet. We have 3 hydrogens that are coupled to our signal, right? This is signal H, A here, and you see a quartet, and so it's going to be, the height difference is going to be 1 to 3 to 3 to 1. You can kind of see that this is a third of the height. So that's just another piece of information that can help you elucidate, right? If you have signals overlapping, and that will increase or decrease those ratios, and so that can be just a tiny little tool. I wouldn't necessarily always look into that. So just the simple fact that we have a quartet is probably good enough to know that if it's spin 1/2, you have 4 or 3 other nuclei that it's coupled to. All right? And so here we have 6, so you get a little heptet. So you have 6 other nuclei, so N plus 1 would be 7. A septet is what they call that. And so sometimes it's hard to see depending on how good your resolution is, how strong your magnetic field is. You might sometimes you just call it a multiplet. And so let's take a look at if it's coupled to two different nuclei that have different strength, right? So the example here is the doublet of doublets. We have a signal, or we have a hydrogen that's coupled to two other hydrogens, but they're inequivalent. So, it looks like they're equivalent, but this is just used as an example. They don't have to be, but if they were different, it also depends on how strong the nucleus is, right? So if this was phosphorus, for example, phosphorus has a spin 1/2, that coupling constant would be much, much stronger. And that's what the J's are. These are coupling constants. And so I'll give you this information here. This is important for you to predict what the multiplet will look like, right? You know you have two nuclei, and they split differently, and so the AC1, okay, the coupling between the hydrogen here labeled C and A is much, much stronger than that to the other hydrogen B here. So what that means is that the large splitting here, and you can draw it like this or from the center to the center, is due to the hydrogen AC coupling, and the small one here is the weaker coupling constant between A and B. So that's also important that you know how it splits, and you can do this one at a time, right? If I didn't give you this, you would simply start with the stronger one, right? So AC, you'd say, okay, HA is coupled to HC, and that is my larger splitting, so HA would be split into a doublet, okay? So this is due to the HA to HC coupling, but then each of these individual doublet, it's not an individual signal, but each one of these lines will then further be split by a second nuclei, but weaker, into doublets. So this doublet gets split into doublet, which gives us a doublet of doublets. Okay, so here we have, and this is where this will come in, right? What I just went through with you. Here we have a signal HA, and it's coupled to two other nuclei. First of all, it's important to note that the JAB coupling here is stronger than the JAC. And that's why the triplet here is further apart. So first it gets split into a triplet. If this was reversed, I'm going to draw it on the left. So there's a single nuclei that's larger. The HA would be split into a doublet. Okay? So here is the J that's the largest. Now, back to this one, and I'll go through this again if you need me to. Right? So the stronger coupling is AB. B has two nuclei, so it's a triplet. And then we have a weaker splitting to HC, and there's just a single nucleus, so it gets split into doublets. So this is why we see a triplet of doublets. If this was the other way around, you would see a doublet of triplets. Okay? Because, right, so if we had this scenario here, where AC is larger, then C splits it into a doublet, and then each doublet splits into tiny little triplets from the weaker coupling, okay? So this is truly important. It will really help you figure out some of these spectra, right? All right, so here are some of the nuclei that we might encounter. So a lot of the important ones have spin 1/2. Hydrogen, carbon-13, fluorine, phosphorus. Those are truly important. They all have spin 1/2, so that makes your life a little easier. I do want to look into, like, boron has two different nuclei. One of them is 80% abundant. They are spin 3/2 and 3. So that will cause different kinds of coupling that I will show you as an example. But you may already be familiar with the splitting of deuterium, okay? And deuterium, which is the nucleus of hydrogen that has a neutron and a proton, and so it has a spin 1, so that's going to cause different couplings. So if, for example, you have a hydrogen or a carbon or anything that's coupled to a single deuterium, what you are going to see is if I is equal to 1, 2 times 1 times 1 plus 1 would then be equal to 3. So instead of a doublet, you see a triplet. And I'm guessing that you've seen that triplet because a lot of times when you do NMR spectroscopy in organic chemistry, you see spectra that are in solvents, in deuterated solvents, right? And so we use deuterated solvents because we don't want the solvent to show us a strong signal, right? So we use benzene, for example, or CdCl3, and so but we do sometimes see a signal, right? So sometimes we are told in proton NMR, you see a long singlet for benzene, it's like at 7.16 ppm, and then you're told, oh, that's just solvent, and I think the singlet for CdCl3 is at like 7 point, also in that same range. I don't remember, but it's in that same range, somewhere north of 7. But you're not really seeing D. You are really seeing H, right? So some of these solvents are 99.98% pure, which means there's just a little bit of hydrogen present, and that can be helpful, right? You don't need TMS as a reference. You can, instead of zeroing TMS or adding a drop of TMS, so you have that 0 ppm signal, you can use benzene or methylene chloride, and there are charts where you can look up what your expected signal is for your solvent, and that can be quite useful. And but what will happen is if you run a carbon NMR, and so carbon 13 is what we use, and you have to collect more scans. If you took a spectroscopy course, you're probably sleeping right now thinking, yeah, I know. But what will happen is you now have a carbon, right, signal. So you have benzene, and you're looking at carbon. Now the carbons are all equivalent, but each of these carbons now has 99% of them are connected to a deuterium, okay? And so you see this carbon that's coupled to a deuterium, and for benzene, you'll see a triplet at 128 ppm. And it's due to a single nucleus, so it's not a doublet but a triplet. And also take note, the height of these is equal to, it's not a triplet that has a 1:2:1 ratio, it's a 1:1:1 ratio because it's a single nucleus. So Pascal's triangle still applies, but it gets a little weird, right? So I don't need to elaborate there. And the same thing is true for CdCl3. You also see a triplet, and it's at 77 ppm roughly. I don't recall. It's also not super important what exactly those shifts are, but I'm just showing you this so you can see that nuclei can split differently depending on nuclear spin. Just to come back to the slide, so I will definitely provide you with not this chart, but I'll just tell you, we're going to do a proton NMR, and then, it's connected to phosphorus. Phosphorus has a spin 1/2, so because it is entirely possible that you have a complex or a compound that is coupled to different nuclei, right? Not just another hydrogen or another fluorine, but also like a phosphorus or a tin or a lithium. So I will indicate all of the active nuclei and provide you with the spin. What you need to remember is the 2ni+1 rule and how that works. And then one last thing before we take a break is that most of the carbon NMR, so you'll see a carbon 13 NMR, and then you'll see these little brackets here like that with another nucleus behind it, and so that means decoupled. Okay, what that means is you're eliminating any kind of possibilities of the carbon signals to couple by proton, which can be very useful because we really are just interested in, here's a singlet, and here's a singlet, and here's a singlet, so this is a carbon, this is a carbon, and this is a carbon. We really don't want to see all of the coupling and multiplets. We just want to know how many carbon atoms are there, and so that's it, basically. Anyway, this was the introduction to it, and when we come back, we're going to look at boron proton NMR and boron coupling, and then later do some variable temperature stuff.